Hello everyone and welcome to my session on scaling test time inference compute and rise of reasoning models. I'm Jayita Bhattacharyya. I work as a data scientist at a consulting firm, and apologies that I couldn't make it to the summit in person, and thanks to the committee members for allowing me to present virtually. So let's get started, and it would be a good idea to start with a meme, and why not? So yeah, I guess LLMs these days are about how at par they can perform with the humans, and that's what this meme says about. It's a common thing that we all do while there's a check box that I will prove that you're not a robot. So that's just this meme is about, is what we are trying to achieve, and someday that will also get passed, I'm sure. So let's discuss about how language modeling actually happens. So essentially, these models are supposed to do a next word prediction for us. So say you have a huge amount of web data that you collected and you intend to train a foundation model out of it. So the very first step or the pre-training step that you take is going to be to take all of this data and train a model out of it, and that model that you get out of it is just supposed to predict the next word, and we call it a base model. Now, this model is not that efficient enough to be given out to the end user. So we do certain other things as well to make it more robust. So the next step of training that we do is known as instruction tuning or supervised fine tuning, where we give in certain kinds of instructions and try to give it some type of answering as to how it's supposed to answer certain questions. So that's how we get our SFT model. And there's a second layer of training as well, known as preference tuning. And the model that we get out of it is a preference tuned model. So this is where you make it more aligned to, as humans, we how we interact with each other. So that's how we get the end state, which is preferably the one that can go out to the user and the user can start interacting with it. So all of this that we discussed is known as train time compute. And over 2024, we have seen that we intend to build these models by increasing the size of the data or the number of parameters that we are giving to the model. And obviously, compute also comes into picture, or the number of flops that are there. So with this, we saw that all of the craze of GPUs that went into training these models over larger course of data, over larger compute power, and that's how we got into this big models. If you see those 600 700 billion and more than that big models that you get, that's how we got it. So these models were working good for us up until a certain point where we saw that it's able to do most of the tasks, such as classification, then summarization, and all kinds of tasks, any information extractions. So it was able to perform well at these tasks, but then again it failed at certain complex tasks, say solving puzzles or math problems. So that's where we had the need for reasoning models. And these reasoning models are capable of answering questions in which require more complex multi-step generation with certain intermediate steps. So this is where we would need reasoning models to be here. And the difference that lies, unlike our regular LLMs, which yield a direct answer to us, in reasoning, we have certain thoughts or processes and reasoning steps to arrive at a final decision. So essentially, if you think of modern day AI, it is nothing but it's supposed to mimic the human brain. Just as we humans, whenever given a problem to go through, there is a thought process we arrive at to. So we need to take certain decision steps, and then only we finally arrive at a question, at a decision. So the same rule applies for LLMs as well, reasoning LLMs. And although it's arguable that how far these models can think and perform, the idea here is that you break down a large problem into smaller steps and then have structured output out of each of them. And essentially, what we do here is that we teach the model in terms of how to answer instead of what to answer. So this is a very great example of GPT-01, which here, if you see, the question is, what is the last digit of 7 to the power triple nine? And the model tries to learn a pattern, that what is 7 to the power 1, 7 to the power 3, 7 to the power 4, and what are the last digits, and sees this pattern of 7931 being recurringly occurring. And thus, it by the rule of modulus, it is able to find that for 7 to the power triple nine, it will be 3. So you see, there are intermediate steps here, which makes the model to come to the final answer. So essentially, these models, if you now have tried out these deep research and model, this is what they do. And there are two ways to go about it. Either it shows you the intermediate steps, what it used to come to the final answer, or it could be that it chooses not to show you and just arrives at the final answer, but the intermediate steps are still there. So over the course of time, we saw that train time compute was working well for us, and then we use certain model scales. We use certain scaling that to increase these compute data set and model size. And we saw that there are these laws of scaling laws, which define that wherever if you want to increase the performance of a model, one of these parameters will be increased, and increasing any one of them will be correlating to the other one as well. Suppose if you want to, if you by any chance increase the compute in any ways, it will affect the performance as well, and so on and so forth. So there have been certain Chinchilla and Kaplan laws, which and the beta lesson as well, which which over the years people have been researching and finding out that this is how we do it. If you want to increase performance, you scale up these parameters to it. So this worked well, but we saw that there needed to be a paradigm shift where these models were not working out that well, and that's when test time compute or inferencing compute came into picture. And essentially, it's where during instead of directly answering out and using not much compute power during inferencing, it deferred to it, and it came up with a concept that why not have more compute power during inferencing and give the model the ability to predict more tokens and then arrive at an answer. So this in compute power inferencing can be inferred in two ways. It can either be that you do it through parallelly or sequentially. So the very basic way of doing is it is through prompting, because it's the easiest method. And if you only in the prompt, if you say that thing step by step, it's the easiest way that you give the model to the ability to retrospect over its outputs, and then it tries to, or if you give some few short examples that given so and so problem, this is how you go about it, this is how you solve it. So that's how this chain of thought prompting came into picture, and it works well for most cases, but might fail. And also it's a conscious call that you need to make, that this won't be good enough for simple Q&As or information extraction, because if you do that, the model will go into hallucinations and it might not answer you correctly. So yeah, this is where you see that reasoning steps I was telling you, that within inferencing it will produce multiple tokens and it will try to pick one of them from each step and go proceed forward to the next one. So that's what this is about, and that's what happens in the runtime when you actually hit the reasoning model, and this is how it generates token by token and then selects one and proceeds forwards. So there are certain search techniques which have been researched over the years, and so essentially it's like, say, two categories that we can divide it into: search against verifiers, which is more output focused in nature. You sample the generations and then select the best answer out of it. The other one is modifying proposal distribution, that is more input focused and trained on the thinking process, how the model exactly you need to tune in the thinking process. So let's discuss them one by one. And the very first one is majority voting. So as the name suggests, majority voting is the very first one, which doesn't use any reward model. Given a set of say given the set of tokens that are generated, the most frequent one is selected. So say suppose I ask what is 1 plus 1, and then the output gives me say just 1 times 1 and 4 times 2 and 2 times 3. So 2 is obvious answer because it's the most frequent one. So it's as simple as that. And before going into the other ones, let's discuss about two major things here. One is process reward model, and the other one is outcome reward model. So, as the name suggests, in process reward models, the process itself is being scored here, and the highest score is selected to be the next one. In the outcome, as it says that it's the only final answer that you score it, and that is being proceeded forward to the next set of outputs. So, in these methods that we are going to discuss here, so we discussed about the majority voting and process reward models and outcome reward models. Majority voting is the easiest one, which doesn't require a reward model, and is also sometimes known as self-consistency, as in a way to emphasize the need of generation of answers, multiple answers, and reasons out of them. So let's move on to the next one, which is best of n samples. And this is the first method where you actually use a verifier or a reward model. This technique generates n samples that uses a verifier or an outcome reward model to judge each answer. Again, you can also do this using process reward models as well, where so you can think of this as there are a bunch of outputs, and that you can think of it as how a tree of thoughts, or say a tree model works in data structures. It has one node and multiple branches coming out of it. So from those, if we go by an outcome reward model, the sampling, and we'll have an output of score from the model, and the highest one is selected as the final answer. In the process reward model, it's like you select you score the total of the each thoughts, and then you arrive at a final answer, whichever one has a maximum score out of them. So the LLM, or as it known as the proposer, generates multiple answers either by using varying high temperature, and each answer is then put through an outcome reward model and scored on the quality of answer. The answer with the highest one is of course chosen. So instead of judging the answer, you could also judge the reasoning process, and then you would use a process reward model for that. And again, the same, the quality of the reasoning step is what is scored, and you pick up the candidate with the highest total one. So this is one way that you can do it. With both of these verifier types, you can come to a weighted average as well, and then also you can pick up the highest total of it. So that would be known as weighted best of n sample. The next one is beam search. So you can do this via process reward models. So the very basic thing is that after you select top three in each of these, you select the top three best candidates from each of these generations, and ultimately you arrive at a final answer. So this of course has multiple reasoning steps and are sampled, and each are judged by a process reward model similar to tree of thoughts if you think of it. And the top three beams or the best scoring paths are tracked throughout the process. This allows in quickly stopping the reasoning paths that do not end up into a fruitful scored by the PRM, and the resultant answers are then weighted using best of n samples. So this is how we do that. Another one is look ahead search, which is very similar to Monte Carlo tree search as well, with some differences here and there. So in Monte Carlo tree search, we try to make the tree more efficient. We have four processes there. The first one is selection. So you select a given leaf node, and based on the predetermined, of course, you have a formula to select that node, and then you expand that, you have additional nodes created, and you have to then roll out or randomly create new nodes until you reach the end. And you also have a backward process or the backdrop to update the parent node's code based on the output. The main goal of these steps is to keep the searching the best reasoning steps that come and while you're exploring the path. It is therefore a balanced method of exploration versus exploitation, and one of the expanded reasoning steps is selected and rolled out multiple times until it reaches to the several answers that we actually need. So look ahead search is often a type similar to it. The only thing is that a more compute intensive variant that performs these k steps rollout to improve the accuracy of the PRM value that is estimated at each step. This is like an upgrade to the Monte Carlo tree search there. So now that we know that this is how we do reasoning process, this was essential to cover because this was a foundation that is used into reasoning models, and we're going to discuss about one of the architectures of such a reasoning model. And you must have guessed it from from this slide. And we all saw what happened January starting this year, and that was the DeepSeek is the first open source reasoning model that we had in front of us, and we saw that it revolutionized the way it did, and we'll discuss about how reasoning is actually acquired. It's very fascinating whatever they did. We'll discuss on it. So and surprisingly they did it again is what I say for this slide. Just like few days back they released a DeepSeek v3.1 version base model, where just a few days back they released another model, and in Hugging Face they released it on Hugging Face, and surprisingly it did not have a model card. Like model card is something where you have the description of the model and everything, so nothing of it was available, and within some hours I saw people downloading the model and then using it. And it's something revolutionizing that people just take the open weights model and start training upon it onto their use cases. So something a bit off topic here, but something good to know here is the compute restrictions that these models have. So essentially, DeepSeek belongs to a hedge fund, and the hedge fund believes to have within 20. So they claim that they did entire this process of training the model within 6 million, and which is a bit weird to believe because they had in US does not allow export of bigger compute engines, which is these H800s and all. It's only H100 or H20s that A100s is or what they have to suffice with. So that's something that there's a company called Semi Analysis. They did these research. They do this research about compute powers, and they brought up this thing that what was the laws before 2022 and after 2025, after DeepSeek came out. So it's surprising to see that they're able to achieve such great results with such less compute. So what magic exactly DeepSeek did, and there were a couple of innovations into the architecture layer that they did, and they went one step ahead of the transformer architecture, the attention mechanisms to prove these. And this was essentially the things that came out of it. So mixture of expert is a architecture that says that instead of having all the nodes activated for your in a deep neural network, you only keep the some of them which are highly active and then move forward with it to it. So mixture of expert existed earlier as well, but there was problems. It used to suffer from knowledge hybridity and redundancy issues. And DeepSeek MOE, which the DeepSeek came out with, is what they claim that they are able to eliminate these problems within mixture of experts models, and they fine-grained an expert segmentation and shared isolation strategy to achieve this. The next step they did was multi-head latent attention, and this was very groundbreaking because when you these models, when you go forward with these reasoning models, a very essential thing is to have a good memory bandwidth, and that's what attention mechanism used to suffer from. But with using MLA, DeepSeek was able to address that memory bottleneck during inferencing without compromising the model quality. This significantly reduced the key value cache requirement during the generation process while maintaining performance and being at par with the attention mechanism. So they also did a multi-token prediction, and of course, we'll be discussing about DeepSeek R1. And they also came up with the FP8 training, which is a very low precision computation, but it was able to achieve high quality as well. Along with this, they also came up with certain other things like dual pipe algorithms, where they achieve parallel distributed training mechanism into the kernel level. They did some hardware. They did very well work in utilizing the entire hardware capabilities, and they considered these compute resources very efficiently. So yeah. Let's as we discussed that this is how the block of transformers and MOE layers come into picture. They also selected the token size to be 130K, where so we also need to look at the tokenizers as well, because that's where our vocabulary is containing, and entire model training depends on it. So every step was very calculated and very well done by the team. So this was one of the benchmark reports that they showcased while they had released the model, and this is like they that time only OpenAI O1 and O1 Mini was out there, and it proved to be very much at par with the performance of O1 onto different benchmarks like AIME and Code Forces, the code ones, the math models, the math data sets, and the MMLU. One thing that I see missing here is the where you actually want to evaluate reasoning models is RKGN. So it is a very great foundation which lays out certain. It's kind of a games that they have into that data set where, and they have a year-on-year competition as well, where frontier labs and researchers do take part to prove how can a model be at par with the humans playing games versus a model playing games. So that's very interesting, and they are later on RKGI did release onto DeepSeek as well. You can check that out. So yeah, so here is the process of how DeepSeek R1 was actually trained. So the very first thing that was done is so they took up the DeepSeek V3 base model, the 671 billion parameter model, which they had released prior to R1, and they take this base model and they do a prompting on top of it. And it's actually interesting how they only do prompting and use reinforcement learning and reward modeling to only get something out of it. This was not attempted earlier, because earlier only certain kinds of reasoning steps were given to the model, and then only it used to learn out of it. But this time they did not use any data set. They used a very simple prompting technique. If you see here, they have a user, they have this prompt where there are answer tags and think tags. Within think tags, the reasoning process is supposed to be mentioned, and within the answer tags, the answers are supposed to be mentioned. So they call it an aha moment, because without even telling the model how to reason it out, just using these XML tags, they were able to achieve whatever they did, and the model did give output onto it. They used two reward models here. One was the accuracy reward, so it ensures that it uses the lead code compiler to verify coding answers, and a deterministic system to evaluate the mathematical processes, so that it ensures that whatever is getting answered is getting answered correctly. And the format reward, so that so it used an LLM as a judge to ensure the responses are expected format, such as placing steps inside these thinking tags. So we saw that what DeepSeek was able to achieve with just prompting and as using some reward accuracy is how it was used to generate this model, which they called DeepSeek R1 Zero. And using this, they generated certain examples of how reasoning steps will be coming. Given a question, there will be reasoning steps and then the final outcome. We'll also be doing it with show so using some. I'll show you that you can also convert any base model or any normal model using GRPO. We'll discuss what GRPO is and convert it into a reasoning model. We'll see that in the demo. Before that, let's see what DeepSeek did. So this DeepSeek R1 Zero model, they used it to generate this SFT, or they call it as a cold start data, because this is not a normal model that they used. They did some prompting and did some reward modeling to generate this model, and which was not done before. So they did this to generate SFT data. So they generated around 600K data from it. One thing that DeepSeek R10 suffered from was the it was getting confused. It was not that consistent in the generation process that it was doing, because it was getting confused in the if you change languages within your question, and within generation also it was getting confused within multiple languages. So there was another reward model that was introduced, which is this consistency model, which would ensure that it has that consistency while switching between multiple languages. And also there was so this 600K data that was generated is this SFT data that you have here, and they generated another set of knowledge data, which they got from DeepSeek v3, and that was around 200k data. So using this 800k data, this data was collected because they wanted to also the model to function for non-reasoning question answers as well, not just answer using reasoning. So they wanted to make it robust in that way. So using this 800k data, they generated this DeepSeek R1, and again there were this rule-based RL verifications as well for math, code, and human preferences. So that's what gave us DeepSeek R1. And another thing that DeepSeek does was distillation using Llama 3 and Gwen 2.5 model. They generated some distilled models. So distillation is a process where you have a teacher model. It is different from the one that is preferably done in deep learning. This is a bit different. So in here, so the knowledge from so this 800k data that was here, this was only used, and in distillation the smaller models learn from the bigger models, so it is trained at a lower precision, but it is as efficient as the bigger models at par, and that's what the DeepSeek report showed us as well, that it was able to achieve performance at pars with regular models as well. Distilled models, however, were a bit big, a downgraded performance than DeepSeek R1, because obviously you cannot compare a small model with such a less parameter model with DeepSeek R1, which is a very very big model there. So but it still is doing well in certain tasks, and if you see this benchmarking results here, you will see that it is being compared with GPT-4o, Claude 3.5 Sonnet, and OpenAI O1 Mini, and it is giving greater results in some of them. So DeepSeek R1 distilled when 32 billion model is performing well. Then, so this is of course varying across data sets and performances. So yeah, this is worthy to be mentioned. Whatever they did to work out to be well. So the one question might arise that why did they want to do distillation, which is only SFT training? So they wanted to test out three things. They first tested out only pure RL, which is that formatting plus the SFT without SFT, just formats, reward modeling, and the prompting that they did. That is pure RL that they did, and they saw that it was giving good results. They got the DeepSeek R10 model, and from there they wanted to see how only SFT or this distillation process worked. So they came to a conclusion that only SFT or only RL is not enough to get a good reasoning model. They tried this SFT plus RL, which gave them DeepSeek R1. That's what is needed for producing good reasoning models, and that's what has proven to be worthy. So we had discussed that how so we kept talking about RL, and we did not mention what exactly optimization technique that they use. So they used this GRPO technique, group relative quality optimization technique. So RL has been in the era for a long time, and you must have seen those Alpha Go and Alpha Zero, all of these gaming things. How it was able to beat humans into how AI was able to beat humans into this games, and we saw there were many preference optimization techniques like RLHF, DPO, PPO, and there's a I could just call it a multiverse, that there is a big model, big policy optimization techniques out there, and in your free time do feel free to go on to and research about it. So let me tell you what GRPO is. So say suppose think of a scenario that you are in a class of 10 students, and you're given a task to bake a cake, and so the outcome here will be that some people will do a very great job, some people might not do a great job, and you are a mediocre student who wants to learn the good things from the best ones who did the good baking, and you want to also learn that what did the bad ones do that did not work out. So you are self learning itself, and you want to go best onto it. So that's what a simple explanation is onto GRPO, is that it optimizes responses by comparing individual response scores to a group average, allowing the model to favor higher scoring responses without needing a separate critic model. So usually in PPO you would need a critic model to give you this, but that is being eliminated onto GRPO, and that's what DeepSeek applied, and they got the results. And we will also see it in a demo in a while. So yeah, let's jump onto the demo, and let me show you how you can also train on any base model to achieve reasoning skills out of it. Training the Llama 3.1 8 billion parameter model using GRPO. So if you see here, you have this, you have Unsloth. We'll be using Unsloth for fine tuning, which is a great library for such tasks. And we also have VLLM. This is useful for better, faster inferencing. But however, I was not able to use it due to compute constraints. But if you have a better compute engine, do try using VLLM, and it will be blazing fast for you. You can do some extra installations if you're using within Colab, and if you're running locally, you can check whatever you need from here from the requirement txt. So there's toss region, bits and bytes, X formers, and transformers that we'll be needing. So let's see how to do this. So very first step is from Unsloth. You can load this fast language model, which will load the model that you need, and you can also set the max sequence length to 1024. You can increase or decrease it based upon your requirements. It can only so this will in turn increase for longer reasoning traces, and this is a debatable topic, like how much you should give and how much less of it would affect the model, or big of it would lead it to overthinking. So on and so forth, you can even think of, and the LoRa rank as well, you can set it up. So for me, if I give it a bigger number, it went on to certain problems. It was stopping the kernel to run it. So this is also a hyperparameter that you can tweak it according to your need. And then we'll load the model from fast language model from pre-train. We'll load Llama 3.1 8 billion instructions PEFT model, and we'll pass in the max sequence length. And so we are loading a quantized model here. So 4-bit model, LoRa model is what we are loading here, and you can set it to false, and it will be 16-bit. However, in Colab using a T4, I was not able to run that, so I turned this onto true. And you can, so if you're using VLLM, you can use it as true. And yeah, max LoRa rank, you can pass in the LoRa rank. And GPU memory utilization, so this also is a is something that was giving me time, and every time it was giving me error, so I had to bring it down to more at an optimal number where it was finally running. And then there are this PEFT model that you can get, and the target modules, which are the target models for this particular model that runs. And so these are the ones you can get a list of it anywhere. And so yeah, we can, so this will load up all the necessary things that you need. The next thing is your prompting and your reward models that you would have to set up. So as you had seen in the DeepSeek R10 model, the prompting technique is the same. You have your reasoning, and you have your answer tags, and you also have your XML CO chain of thought prompting. So we want our reasoning to be enclosed within this reasoning tag. We want our answer to be enclosed within this answer tags. And these are some helper functions to load your dataset onto. And we'll be using the OpenAI GSM 8K dataset. So if you check the dataset into Hugging Face, it's present there. So it is a high school level mathematics question answer dataset where there is question and there is this explanation of how the answer is coming and the answer at the end. So that's how it is. And then you do basic role system and content system prompt, all of those things you do. So essentially, whenever we want to build a reasoning model and want to use reinforcement learnings, we have to set up our reward functions. So 6 reward functions have been used here: continuous reward function, integer reward function, strict format reward function, soft format reward function, count XML. So these and another one is also here. So these are the ones which based on the output of the model, it's either being penalized or being rewarded, and each of these has its own logic that is built into it. So although you can experiment by only so you can use two at first instead of using all 6 at once. You can try with 2 of them once: the correctness reward function and strict format reward function. So these are the 2 essential ones that you will need it, that how accurate your answer is and what format of your answer is. So that way you can test it out, and then if you think that you need the rest of it, you can again plug these up. So next is so we load up the GRPO trainer, and from the TRL library we have this GRPO config model that will be able to load it up. So here again, there are certain parameters that you can tweak in. Instead of using paged Atom 8-bit, you can only use Atom. So LR scheduler type, you can give it to cosine, I would say. And yeah, maybe keep these type of parameters as it is. You can tweak a bit and check if you're that curious. But yeah, so one thing that is essential here is for device train batch size. So again, due to compute restrictions, I had to lower it down, and you can check out what works best for you. If you want a full training, turn this num train equals to 1. And be careful that gradient accumulation steps is you can increase it to the power of 4, and that's how that would go ahead. So ideally this is running for a 250 epochs. If you see the output here, it will run for at least 250 epochs. So these models won't give you a good result if you run it for 100 or so. It's working best if you increase it up to 200, 250 ideally. Then only you'll be able to see some results there. If you want how the training performance is going on, you can plug it up to 1B, which is the observatory platform. You can just change it to 1B. You would also have to pip install 1B. So that way you can do and check up how the training process happens with the increase and decrease in curves. You can check those out. Since here in the training, after a lot of at the last phase of it, it changed to the KL divergence changed a bit. At the end, you see a 0.5 here. So yeah, that's how it is getting trained, and the rewards also, if you see, it is penalizing here. So on and so forth, you can do that. So finally, we start the training, and we pass in the model, the tokenizer, and the reward functions, and the data set, of course. And if you see here, it started training, it taking in the questions and answers, and it has a detailed report of all those 250 steps that is going. And towards the end of this training, if you see, there will be these reasoning tags and answer tags appearing. Let's look where it is towards the end, because initially it would not learn. Also to note that while we are feeding in the dataset, we're only giving it the question and the answer. We are not giving the reasoning steps to the while in the dataset. We are excluding that part because we want the model to come up with those reasoning steps. So if you see here, this is the answer tag within which it is coming up, and let's see if there is a reasoning tag there. Okay, maybe towards the more end it is appearing. So this is a long process of 250 epochs that it has run, and the training process has happened. So from that, it's towards the very first 100 and 150 epochs, it would not learn to include those. It's only up until after that later epochs it is trying to learn it up. So okay, maybe you can check this up. Okay, I see one reasoning tag here. Yeah. So after plenty of epoch runs, it's finally learned to bring in this reasoning tags and this answer tag itself. So that's how it has been able to learn it up, and then you can do inferencing out of it. So you first check it out. So how it without the load of fine tune model, the only base model, how is it performing? So you see here, there's no reasoning steps or anything. It's just trying to answer whatever is being asked here. But then you save the LoRa model, and then you do an inferencing out of it, and then you see that there are these reasoning tags being appended to it, and the answer tag as well, and that's how it is giving you an answer. Now you cannot debate much on the accuracy of this system, because this is just to show you the art of possible on how these, and you can turn any model into a reasoning models, and then yeah, you can test it on your own onto the next steps. So we are very much on towards the end of our session, and these are some of the things that I would like you to take back from the session. As it is like it's not possible to cover each and everything that I just discussed. Each of these topics that I discussed needs an individual session of their own, because it's a really vast topic, and within RL as well, if you see, it's a wide area of exploration. And throughout the next year, I expect that it will be so that we apply more of RL to achieve better reasoning capabilities. So one thing to note here is that this is a funny slide, and I just wanted to keep it so that you recall that not everywhere we need reasoning models, but into certain complex tasks, maybe if you're doing agentic reasoning or any autonomous system that you're building, then it makes sense. But if you're building simple information extraction systems, then it might not be the case that you need reasoning LLMs to use. So make that conscious call, because you do need to think of the number of tokens that are going in, the cost per token if you're using a closed model. Also, if you're using an open model, there's this compute power that you need to think of. So all of these things come into picture, and you need to be aware of it. Certain ideas that I have been exploring is that about hybrid LLMs. Like, so this was an idea by Google. I came across their video where, onto Edge AI. There has been a lot of work being done on Edge AI, and then they come up with a concept that for, because in Edge you need to very you need to run systems on less compute and faster inferencing. So for that they do a switching between Gemini and Gemma based on the question being asked. It will either go to the cloud-based model or the local model based on the queries that is being asked. So I thought of, why not that can be done for regular versus reasoning models as well. And can we switch based on the question? Can we switch whether we need a regular model to be answered or a reasoning model to be answered? Because if you used reasoning models onto normal tasks, it will might be hallucinating and not giving you the correct answer. And for reasoning based tasks, if you use regular LM, that is also not correct, because you won't get the correct answer out of it again. So this is just an idea, and I'm also exploring it. And if anybody comes up with any answers, do let me know. Have to hear it out. And another thing that is going to be revolutionizing is this. There's a paper by from NVIDIA. They came up with that will small language models be good enough for agents and reasoning? So yes, onto certain tasks, if you have specified niche business areas where there is only a single problem statement to be fit, not generalization as a whole. So there you can fine tune these SLMs using RL and reasoning models to bring out agentic behaviors. This paper is really nice to give it a read. Yeah, you can maybe scan it if you want to get access to this deck. And these are some of the resources that I've been using. These are from very good research and frontier labs that I've got into. And yeah, you can explore more things, because yeah, it's a vast topic. And if you go into YouTube, I'm sure you will find out 50 and hundreds of more videos onto it. So yeah, this is all from my side. And if you have any queries, to reach out to me on my socials. I'm happy to answer and brainstorm more use cases onto it. On that note, thank you so much for hearing me out. And yeah, goodbye.